Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into a fascinating debugging saga involving a Linux kernel performance issue. It all started with listen overflows on our Apache web servers, a real nail-biter.
Listen overflows? What exactly are those, and why the excitement?
Right, so listen, overflows happen when Apache receives web requests faster than it can process them. The request queue fills up and overflows, leading to dropped requests and, you guessed it, slow page loads. A major headache for any web server.
I see. So the problem was tied to an OS upgrade from CentOS to Ubuntu, right? A kernel version bump from 3.10 to 6.8?
Exactly. The upgrade triggered a surge in these overflows, especially after new servers joined the pool. Initially, we suspected network issues, classic debugging gut feeling, but the network packet captures told a different story.
So it wasn't the network? What gave it away?
Well, Strace, PHP spy flame graphs, and even Wireshark showed seemingly slow network operations. But deeper analysis revealed normal network latency. The problem was actually on the server side, a huge system CPU spike.
A CPU spike? That's a pretty clear indicator of something else going wrong. What was the culprit?
That's where it got really interesting. The spike was linked to the inode switch WBS work FN kernel function, part of the inode Cgroup switching mechanism. This function handles moving inodes between Cgroups during writeback, and it was completely hogging the CPU.
Inode Cgroup switching? Could you explain that a bit more? I'm not familiar with that.
Sure. Think of Cgroups as resource containers for processes. Inodes, which hold file metadata, are assigned to the C group of the process doing most of the writing. When a process finishes, its F group is removed, and its inodes need to be reassigned. This reassignment, in our case, was causing the bottleneck.
So the thousands of files written during the server bootstrapping process were triggering this massive inode reshuffling? And that's what caused the CPU spike?
Precisely. We used BPF trace to confirm thousands of inode switches during the CPU spike. It was a beautiful moment of clarity. The fix was surprisingly simple, though.
Simple? After all that?
Yeah, we disabled the I/O and memory controllers in the system slice used by the bootstrapping process. This prevented the unnecessary C group accounting and inode switching. Problem solved.
Wow, that's a fantastic example of how deep debugging can lead to surprisingly simple solutions. So CentOS wasn't affected because it used Cgroups v1, which doesn't have this issue?
Exactly. Cgroups v2 introduced these controllers, and the problem seems to be specific to that version. We even created a minimal reproduction script using dd and split to generate a bunch of files, triggering the same CPU spike. It's a pretty robust reproduction, I must say.
Amazing work! So what's the takeaway here? Besides the obvious need for thorough debugging?
Well, always consider the kernel as a potential source of performance issues, especially after OS upgrades. And don't underestimate the power of tools like BPF trace and perf for deep kernel analysis. They are invaluable for this kind of work. And of course, always check your Cgroups.
Absolutely. Thanks for sharing this incredible debugging story. It's a great reminder of the complexities of modern systems and the importance of systematic troubleshooting. This was a wild ride.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Thanks for listening, and we'll catch you next time. Goodbye.
Bye-bye.